Injection molding is the most common method for mass manufacturing plastic products. Examples include chairs, toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops the plastic product. In reality, injection molding is an intricate, complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bags wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it ramps forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute, the mold opens, and the part is ejected. The mold then closes, and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment and coloring, or with up to 15% recycled material and fed into the injection molding machine. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath the surface of the material. After the injected part solidifies, the mold opens. As the mold opens, the volume increases without introducing air, which creates tremendous suction that holds the mold together. So at first, the mold slowly opens several millimeters to allow air to rush in and break the vacuum, and then the mold quickly opens the rest of the way so the part can be removed. These precision machined steel molds can cost hundreds of thousands of dollars. Removing the part from the mold can be difficult. When the plastic cools, it shrinks and so becomes stuck tightly on the core half of the mold. Molds have built-in ejector pins that push the part off the mold. The ends of the pins sit flush with the core half of the mold, but are not perfectly aligned. Sometimes they protrude or are dented slightly. So, if you look closely, you'll see circular ejector pin witness marks on molded products. For example, this chair on its bottom has an array of witness marks. When the part drops from the mold, an operator has to remove the screw, that section of plastic that connected the injection unit to the mold. Screws are manually twisted or cut off the part. Screws are attached to objects only in molds that make a single part at a time, like a chair. Smaller objects are made in multiples of a single mold. In these, the screw connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the screw, connecting each cavity in the mold via a small, typically rectangular entrance called the gate. You can see the gate on plastic cover. The parts from model planes typically come still attached to their runners. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. Here on this piece of cover, you see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor do they have sharp corners. This creates a noticeable parting line on the molded object. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject because its inner walls will scrape the core half of the mold. Also, the vacuum will be difficult to break because air cannot readily enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed because once the part moves slightly, the walls are no longer in contact with the core half and air can rush in. One impressive example of injection molding is the Lego brick. You can see the injection point in the middle of a stud, but this is not from a gate or a sprue. The Lego molds use hot runners. Hot runners are a heated distribution network. This keeps plastic inside the runners molten, while the plastic in the mold solidifies. This leaves no gates or sprues to be removed. The molded bricks are ejected and ready to use. The downside is that this setup is more expensive than a traditional cold rubber system. On the bottom edge of the brick, you can see ejector pin witness marks. And what's most clever to me is where Lego designs their draft angle. The outside of a Lego brick must be square. So if you cut a Lego brick in half, you can see that these inner supports are thicker at the top than at the bottom. There's a draft angle of about 1.5 degrees. This helps the ejector pins push the brick off the mold. core half and the cavity half of Lego molds are designed so that the parting line is at the bottom edge of the brick. This hides the parting line. Look around you and see how many injection molded objects you can find. Likely the device you're watching this on has injected molded parts.